Hey, cheesebacks. To add to our understanding of different theorems about the polynomial zeros, I want to talk first about Descartes' rule of signs, okay? And so the first thing I want to talk about is the number of positive real roots of the coefficients is the same as the number of sign changes in the original polynomial that's in standard form. So then the number of sign changes. And then I reduce by 2, and I'm going to explain that in a second. Reduce by 2's. And then the number of negative real roots is the number of sign changes, again, but now it's of negative x. So of f of negative x. And I'm going to reduce by 2's again. Reduce by 2's. I apologize for my handwriting. So let's see this in action, and maybe it'll make more sense. So let's start, let me get my highlighter out, with the positives. And so what I'm going to do is I'm going to count every single time the sign changes. So I started with a positive. That's a positive number. So I went from a positive to a negative. That is one sign change. And then I went from a negative to a positive. That's another sign change. And then I went from a positive back to a negative. That's another sign change. And I went from a negative back to a positive. That's another sign change. So that's 1, 2, 3, 4 sign changes. So I would have 4 as a maximum of real zeros. I also have to think about imaginary zeros for a moment and realize that those always come in conjugate pairs. That's what we talked last class. So this is how many real zeros I have. Well, what if I have some imaginaries? Well, if I have one set of imaginaries, I would have 2 possible real zeros. And then if everything's imaginary, I have no real zeros. So that's what I mean by reduced by 2. I have to think about what would happen if I had some imaginaries. All right, let me erase my sign changes here. Ooh, that's just gross looking. I apologize. Let me see if I can clean that up a little bit better. Okay, so now let's talk about the negative. So I'm going to go ahead and take this, and I'm going to change all the x's to negative x's. So negative x to the 4th minus 5 negative x to the 3rd plus 7 negative x squared minus 5 negative x plus 6. And so we're going to change the signs of things that need to change. So anything with an even exponent is just going to go back to what it was because they're going to cancel, the negatives are going to cancel each other out when I multiply. So it's going to become x to the 4th. This one right here, though, this negative x to the 3rd becomes negative. And so now I have a negative times a negative. That's positive 5x to the 3rd. Remember, we've talked about before, everything with an odd degree is going to change signs. So now I have 7 times negative x squared. Well, negative x squared is just going to cancel each other out, and so I'm just going to get a positive x squared. Here I'm going to get negative 5 times 5, which is a positive 5x. And then the constant's a constant. It's going to change. It's not going to change, pardon me. Well, if I look, none of my signs change. So I don't have any negative real zeros. Okay? And so over here I have this imaginary situation that I want to talk to you guys about. So my degree here is 4, which means I have 4 zeros. Some might be real, some might be imaginary, but I'll have 4 of them. And so I can think about all the different scenarios of the different types of zeros I can have. So if I end up having 4 positive real zeros and no negative real zeros, well, I can't have any imaginary zeros because this has to add up to 4. I have exactly 4 zeros. That's the fundamental law of algebra. I'm not going to have any real zeros because my signs never change. Over here, if I have 2 positives and no negatives, that means that everything left over has to be imaginary so that I get to my 4. And then lastly, if I have no positive real zeros, no negative real zeros, that means everything must have to be imaginary. So it comes together to be 4. We're going to be practicing this in class. I just want to show you that's how I can tell using Descartes' rule of signs how many positives, negatives, and imaginary zeros I have. The other theorem that I want to talk about today is the rational root theorem. The rational root theorem is just a way to get a list of all of the possible real zeros. Rational real zeros. Rational just means it can be written as a fraction. So no square roots, no irrational numbers. Pi is not going to become a part of this. So to find out all of the possible rational roots, I have to do a little formula. And it's not too bad. So P is all of the factors of the constant. Factors of the constant. And I don't know why it's P and Q. It just is. And then Q is all of the factors of the leading coefficient. I'm not going to write out leading coefficient, of the leading coefficient. So let's figure out the factors of the constant first. So I have this example here, and it looks like my constant is right here. It's 36. So I have to think of all the numbers that go into 36. So like 1, 2, 3. That's a horrible 3. 4. 5 doesn't go in. 6 does. 7 doesn't. 8 doesn't. 9 does. 10, 11, 12. 12 does, doesn't it? 13, 14, 15, 16, 17, 18. What I'm doing is, oh yes, and then of course, 36. So let's just double check ourselves. 1 times 36 is 36. 2 times 18. 3 times 12. 4 times 9, and 6 times 6. Okay, there's all my list. The big thing here is I have to remember that these would all be considered pluses or minuses. So I would have, so now my list on the top is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Ooh, I'm going to erase that. That's just terrible handwriting. I'm trying to be neat. Plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18, plus or minus 36. Whew! Now, I do the same thing, but I figure out the possible factors of the coefficient. So my coefficient here is 2. My leading term is x to the third. Its coefficient is 2. Well, that's a lot easier. That's just 1 and 2. Those are all of the numbers that go in. So I would divide everything by 1 and 2. I'm going, my gosh, this is such a long list. I know. So let's deal with all the things being divided by 1. Well, that means those numbers aren't going to change. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18, plus or minus 36. Goodness gracious. Let's keep moving it up. All right, so I've dealt with everything being divided by 1. Now I have to deal with everything being divided by 2. So 1 divided by 2 is a half. 2 divided by 2 is 1, and I already have that written. 3 divided by 2 is 3 over 2. 4 divided by 2 is 2, and I already have that one. 6 divided by 2 is 3, and I already have that one. 9 divided by 2 is just 9 divided by 2. 12 divided by 2 is 6. I already have that one. 18 divided by 2 is 9. I already have that one. 36 divided by 2 is 18. I already have that one. So this long list is all of the possible zeros. That's why Descartes' rule of signs is so helpful. It helps me realize if I didn't have any negatives, I'm going to get rid of all of that. I'm just going to use that real quick just to kind of show you another Descartes' rule of signs, because I know that that part can be pretty confusing. So let's look at our original problem over here. I'm going to here, I'll move it over and I'll rewrite it. So I have 2x to the third minus x squared minus 27x plus 36. How many times did the signs change? Well, I went from a positive to a negative. That was one sign change. I went from a negative to a negative. That didn't do anything. I went from a negative back to a positive. That's another sign change. So I have at most 2 positive zeros. And if I go down by groups of 2, in case I have, imaginaries, I could have no positive zeros. So thinking about how all of my odd degrees will change signs, I'm going to change the sign of my odd degrees. And I'm going to keep my even degrees the same. I'm just going to change the signs of these 2 odd guys right here. And now I'm going to count my signs. Well, let's see here. Negative to a negative isn't a change, but negative to a positive is. And then positive to positive isn't a change. So I have at most 1 negative. If I have 1 negative, I can't go down a level at all. I have to have 1 negative. If I go down by 2s, well, that's not possible. I can't have a negative. That just doesn't make any sense. So I have 2 positives and 1 0, and 1 negative 0, or I have no positives and 1 negative 0. So this is a degree 3. So that already equals 3, so I'm good to go. But what about this guy? This is saying I have 0 positives. I have 1 negative, which means the imaginary side of things, I must have 2 of them, because it would have to add up to 3. So we're going to be practicing with this in class, but I just want to give you a little heads up on this. Stay fresh, cheese bags.